Independent and dependent variables. Verify that dy over dx times dx over dy equal to 1 when y equal to x power 3. If y equal to x power 3, then dy over dx is equal to 3x square. If x equal to y power 1 over 3, dx over dy is equal to 1 over 3x square. Therefore, dy over dx times dx over dy equal to 1. Switching variables in differential equations. Dy over dx equal to f of y by implies dx over dy equal to 1 over f of y by implies x equal to integral 1 over f of y dy. A hot air balloon can reach a maximum height of 1.25 kilometers at the rate at which it gains height decreases as it climbs. According to the formula, dh over dt equal to 20 minus 16h, where h is the height in kilometers and t is the time in hours after liftoff. How long does the balloon take to reach a height of 1 kilometer? dt over dh equal to 1 over dh over dt, which is equal to 1 over 20 minus 16h. So t equal to integral 1 over 20 minus 16h dh. Since only the time at h equal to 1 is required, you need not find the general equation connecting h and t. Instead, you can find the time at a definite integral from h equal to 0 to h equal to 1. So integral 0 to 1, 1 over 20 minus 16h dh is equal to, after simplifying, you get 1 over 16 log 5, which is nearly equal to 0.1. The balloon takes 0.1 hours or 6 minutes to reach a height of 1 kilometers. When a ball is dropped from the roof of a tall building, the greatest speed that it can reach, called the terminal speed, is u. One model for its speed v when it has fallen a distance x is given by the differential equation dv over dx equal to c times u square minus v square over v, where c is a positive constant. Find an expression for v in terms of x. The given differential equation is dv over dx equal to c times u square minus v square over v, where c is a positive constant. Dx over dv is equal to 1 over c times v over u square minus v square. X equal to integral 1 over c times v over u square minus v square dv. Writing the integrand as minus 1 over 2c times minus 2v over u square minus v square. Note that v must be less than u, so that u square minus v square should be greater than 0. The second factor has the form f dash of v over f of v, where f of v equal to u square minus v square. Therefore, x equal to minus 1 over 2c log of u square minus v square plus k. The ball is not moving at the instant when it is dropped. So at the instant when it is dropped, v equal to 0 when x equal to 0. The initial condition gives an equation for k. So by substituting those values in the above equation, we get k equal to log of u square minus 2c. The equation connecting v and x is therefore x equal to 1 over 2c log of u square minus v square. You must now turn this equation around to get v in terms of x. So 2cx equal to log of u square over u square minus v square. U square over u square minus v square is equal to e power 2cx. U square equal to u square minus v square times e power 2cx. And after simplifying, we get v equal to u times square root of 1 minus e power minus 2cx. A steel ball is heated to a temperature of 700 degrees Celsius and dropped into a drum of powdered ice. The temperature of the ball falls to 500 degrees in 30 seconds. Two models are suggested for the temperature T degrees, capital T degrees after T seconds. The rate of cooling is proportional to capital T, and B is the rate of cooling is proportional to capital T power 1.2. It is found that it takes a further 3 minutes for the temperature to fall from 500 to 100 degrees. Which model fits this information better? The rate of cooling is measured by dt over dt, and this is negative. This model is described by the differential equation dt over dt equal to minus a times t, where a is a positive constant. Inverting, we get dt over dt equal to minus 1 over at, which has a solution t equal to minus 1 over a log of t plus k. Since t equal to 700 when t equal to 0, substituting those values, we get k as 1 over a log of 700. So t equal to 1 over a log of 700 over t. The value of a can be found from the fact that t equal to 500 when t equal to 30. So substituting those values, we get a as nearly equal to 0.0112. For model B, dt over dt equal to minus b times t power 1.2. So dt over dt equal to minus 1 over b t power minus 1.2, and t equal to 1 over 0.2b t power minus 0.2 plus k. From the initial conditions that t equal to 700 when t equal to 0, by substituting those values, we can find the value of small t equal to 5 over b times t power minus 0.2 minus 700 to the power of minus 0.2. From the boundary condition that capital T equal to 500 when t equal to 30, we can find the value of b, which is nearly equal to 0.00313. The figure that has been shown, it shows the two models to be compared, whose equations are given below. That is capital T equal to 700 e to the power of minus 0.0112t, and B is capital T equal to 1 over 0.000626t plus 0.270 to the power of 5. To choose between the models, use the other piece of data that capital T is equal to 100 after a further 3 minutes, which is when t equal to 30 plus 180, which is 210. Try putting t equal to 100 in the two equations. Model A gives small t equal to 174 and model B gives small t equal to 205. This suggests that model B is the better model. The equation for exponential growth: if dq over dt equal to aq, where a is a non-zero constant and q equal to q naught when t equal to 0, then q equal to q naught e power at.